So you may have noticed that the server is down. Unfortunately, it was hacked, and so we have to shut it. It's something that we run private, not part of IT, so we have to shut it down. We have to figure out what we can do. In the meantime, I'll send you materials that we need over the email, but Lana and I are working on a solution. We have a YouTube channel, and we'll move the videos there for now. Think about it going forward. All right. But if there's anything you need that you don't have access to, email it. So we have a problem set coming up. I'll have my usual office hours this afternoon. I do want to try to think about a time to schedule a makeup lecture for the lecture we missed last Wednesday. But I'll say, we're just off the cuff here. Is it possible? I mean, I know I see a lot of people that want to hang out right after class and you're not rushing off. If we extended a Monday class, could we have class continue? Does anyone have a conflict at that time? Your conflict? Okay. We'll see what we can do. We'll see what the minimal conflicts are. But that would be my preference. I don't think there's anything in this room, and we can just keep going for a little bit, take a break, and have more interest. All right. All right, very good. So, we've been talking for many weeks now about two-level atoms. And today, wait for it, we're going to talk about three-level atoms. And I promise we'll stop there. There's some very interesting, important phenomena that are associated with having more than just two discrete quantum states that we are trying to manipulate quantum coherence within. If we have a third quantum level, the kinds of quantum coherent phenomena that we can get are different and interesting. So there are different kinds of configurations. What we're talking about is, so we want to think about generally the situation where we have some laser fields, and I'm putting laser in quotes because it might not necessarily be an optical frequency. We could have a microwave frequency or some other electromagnetic waves, but we're really, for the moment, thinking about restricting ourselves to the question of optical information. So we may have, what kind of situation why we might want to do this, and where three levels? Well, as we have discussed, we're typically thinking about optically allowed transitions, meaning when I say allowed, what we mean is they're electric dipole. There's a dipole selection rule, which means this is what we call allowed transition. If it's not electric dipole, it might still be possible to drive that transition, but it's a very weak transition. Very hard to drive those transitions. So you remember we talked a little bit about selection rules that you should have learned about in 521, 522, if you took that course. But anyway, now the problem with that, as we know, is that because that transition is allowed, meaning we can drive it with a relatively modest intensity, it also means that energy level can decay very rapidly back to the ground state. And in a typical optically allowed transition, that lifetime will be a few nanoseconds. Which means if we want to drive coherence in that system, we need to have the Rabi frequency extremely strong. We need a lot of intensity to get coherence before the system decays, and then it doesn't last long anyway. So driving quantum coherence and creating quantum superpositions where your excited state is very short-lived is not a good strategy if you want to, say, encode a qubit in the levels, right? But if you want, but you still might want to manipulate your qubits with optical frequencies, because lasers are nice sometimes. So we might have a situation where we would like instead to think about our two levels, our qubit, as states that are very long-lived, that don't spontaneously decay. For example, we might have a situation where we have two levels, I'll call them 1 and 2, or they could be 0 and 1, which are both sublevels of an electronic ground state. So I might have a situation where two of these levels might be two magnetic sublevels. Remember, there are many quantum numbers, LL, and there are the different M quantum numbers. So these are both in the electronic ground state. Maybe they're split by, they're split by the hyperfine splitting in the ground state. But they're all in the electronic ground state. Okay, they're split by some energy, but that energy is a small perturbation, say, due to nuclear spin. Okay, so I might want to drive quantum coherence between that, but these two states being in the same L, say they're S states, are not, I can't drive them with an electric dipole transition. But I might have some, so then I have some third level up here. Here's my 3-level atom, where I can drive optically. This is an optically allowed transition, and this is a different optically allowed transition. They're, in this case, they might be degenerate or they might not. And I might want to drive a situation like this, where I have two laser frequencies, omega laser 1 and omega laser 2, which are near to resonance with some detuning delta to that excited state, okay? So this is an example where I might be able to, as we will see, manipulate the quantum coherence in these two levels via a third level without going directly between them in some transition, okay? Or it might be that the two levels look like this, and they're metastable, maybe to some ground state, and I have a transition, something that looks like that. This has the very evocative name as a lambda configuration. And this is known as the V configuration. Because, guess why? Anyone have a guess? This is a lambda and that's a V, right? So if the two states are that you're connecting that way through this kind of transition, we usually separate them. This spatial separation means nothing except that we can draw it. We call it the V. Or it might be the case I have something like this, where the intermediate level is in between the two. So this might be an S state, this a P state, and this another S state, for example. okay? And I might have something like this. Okay. This is known, this doesn't have a fancy letter, this is known as the ladder configuration. This kind of configuration. All of these are examples of what we call two-photon resonance. So from the point of view of thinking about this in terms of rate equations or Fermi's golden rule kind of picture, there's a rate of transition to go from one, but not through absorption of a single photon, but through, it absorbs two photons. And you might say that there's a virtual excitation into the intermediate level. I don't like that number so much, but I don't know what that really means. It's the Schrödinger equation. This is a kind of configuration that is used all the time these days. For example, this might be a very, very, very highly excited state to a very high principal quantum number. Say this is, you know, in my favorite atom that I know is cesium. This, the ground state, has principal quantum number 6. This might be principal quantum number 70. This state is known as the Rydberg state. It's a very high line state, and as you may remember, if you look at the expected radius of the atom, of the electron from the nucleus, it goes like the principal number, quantum number squared. So, you know, in this principal quantum number, the electron is so far from the nucleus, it's like, you know, a micron from the nucleus. It's barely a bound, it's barely an atom, but at that point it's extremely polarizable. And so you can manipulate that with another nearby atom, and that's a hot topic these days in atomic physics. But it's, you know, but you can't excite it directly. If you want it to be an S state, if it's a P state, you could do it directly with a UV laser. But if you want it to be an S state, and there are reasons why you might want to do that, you would do it through a two-photon transition of this sort. And then try to manipulate the coherence there. Okay, so this is my motivation slide. This is why we're talking about this kind of thing. And it's done all the time. If we really want to manipulate quantum coherence with lasers, then we need to do this because otherwise the lifetime is going to be too short if we do it as a two-level system. Okay? All right, so with that said, we want to now think about the dynamics associated with this kind of system. Okay? So let's look at the situation where, I mean, let's focus, for example, on this kind of situation. By the way, before I do that, I should say something about this kind of lambda configuration. In sort of very traditional spectroscopy, there's something known as Raman scattering. So in Raman, you know, this was discovered God knows when, in the late 19th century, early 20th century. The idea is that you shine light on something, and of course they didn't know about energy limits back then. This was one of actually Einstein's motivation for the invention of the photon. You can have a situation where you send in light at one frequency and you have a Stokes scattering, where this photon or the light that's scattered has a frequency that's less than the
incident photon through this kind of absorption and re-emission. Or it could go the other way and it would be anti-Stokes scattering. And if I put on another laser beam at a different frequency, I can get stimulated Raman scattering. Okay? But again, that's a very rate equation-y picture of thinking about stimulated emission and going from here to here, and not thinking about the quantum coherent evolution and the kind of Rabi problem that we saw in the two-level system now extended into this three-level system. Okay? So let's write down, let's think about that, and let's think about this kind of system. Okay, so let's think about our boundary configuration, although the same mathematics applies in any of these configurations. Okay, so the first thing I want to do is I want to think about, we're going to include the possibility of spontaneous decay of the excited state. The excited state can decay with some rate gamma. I'm not saying what the branching ratios are, whether it goes here or to any other states. It can go to multiple states. That state, excited state 3, has a finite lifetime, and its spontaneous emission rate is 1 over that lifetime. We'll call that gamma. All right? So now I want to write down the effective Hamiltonian for this three-level atom, which includes spontaneous emission. Okay? So it includes the finite lifetime. And so we're going to drive the system now again, I want to emphasize, I've drawn these and we'll think about these as at themselves separated in energy by some amount, but I don't have to have that. These two levels might be degenerate, and then these two laser fields would be at the same frequency. What would distinguish them would be their polarization. So I can have a selection rule depending on the polarization of the light that connects this state and this state, and a different polarization of light that connects this state and that state. Okay, that's possible and done all the time. All right. So with that said, let's write down what the effective Hamiltonian is in the rotating frame. Okay. So we have these two laser fields, and we want to think about the atom-light interaction Hamiltonian, including, right, so this is going to be, involve the atoms Hamiltonian, the atom-light interaction Hamiltonian, and then we go to the rotating frame and we subtract off the fictitious magnetic field. Right? So what do we have in that case? Well, we're going to have something related to the detuning of the excited state. So that's that guy here, the excited state in the rotating frame. Its energy is subtracted off by the detuning. And then it has a finite lifetime. So that's the Hamiltonian component associated with level 3. Then I have, let me just make sure I'm going to keep my notation straight for my thingamaboozies. Oh, I skipped the whole thing. Let's come back. Hold that thought. I'll come back to this. Because there's a very important piece of the lecture that I forgot about, and I need to do before I get to that. Let's rewind a bit. We'll edit the video. And then after we talked about Raman scattering, the most important thing to talk about is the problem of adiabatic elimination. So let me explain what I mean by that. All right, so let's go back to our two-level atom. So my two-level atom, and this has some spontaneous emission. Okay, so now let's write down my two-level atom effective Hamiltonian. And so this guy is going to be, there's some detuning. We have some Rabi frequency. My effective Hamiltonian in this case. So the excited state in the rotating frame, okay? In this case, I've taken the ground state to be at 0 energy. The excited state to be at some energy. If I go into the rotating frame, I get the energy of the excited state minus the frequency of the laser, which is minus the detuning. Okay, so that's that term. And then it has a finite lifetime, right? And we know this is what we should add. The gamma over 2 is because the probability decays at gamma. The probability amplitude decays at gamma over 2. All right? And then I have the Rabi frequency. So this is the d dot E term. And that, for 0 phase of the laser, gives me the off-diagonal elements that couple the ground and excited state. Right? You with me? Okay. So what we want to look at is the dynamics of this situation. We want to consider the dynamics when the detuning and or the lifetime are, this is much, much bigger than omega. Mostly what that means is that we're sufficiently far of resonance. So, if I write this down, thinking about the effective Hamiltonian part of the dynamics, not thinking about the refeeding part, which we know is part of the master equation, then we can just look at this as a Schrodinger-like equation. Okay? So I have my equation, which is the time-dependent Schrodinger equation, but now with a non-Hermitian Hamiltonian, ignoring the refeeding part. Okay, so let's look at the equations of motion for the probability amplitude. So we'll write the general state as in the probability in the basis of my two-level atom. So what do I get? I get that the excited state decays, evolves according to I delta minus gamma over 2 E minus I omega over 2 CG. That's just using this equation and taking the matrix element of it by projecting it onto the E. And similarly, the ground state evolves like that. So those are the equations for the probability amplitudes according to the effective Hamiltonian. It's the Schrodinger equation with the decay term in it. Okay? Now this equation we can solve formally. We can write down a formal solution of this ODE. That is to say, I want to write I want to just write using the Green's function for this ordinary differential equation, just write down what the solution is as a formal solution. So there's going to be whatever the initial condition is, and then there's going to be the term that depends on how it's coupled to the ground state. Yeah.
So if you take the derivative of the thing, you can turn it into a linear differential of just one variable, and then there's a known form for that. So like if you do like
Right. I can try to decouple them. But I want to find an approximate solution, which I can do by just looking. I can think about this as, this is like a forced oscillator. So this is like the homogeneous term, and this is like the forcing term. And if I didn't have this term here, there would just be an exponential, right? But the general solution to this, the Green's function for this guy, is just that. And then I have times that. That is the formal solution to that ODE. This is the Green's function of that ODE. So if I had a delta function here, then I'd get this kind of ringing response. What you're saying is correct, Matt, but this allows me to write down an approximate solution, which is what I'm really interested in here. Okay? You can check for yourself that when you take the derivative of this, you get that. Everyone should learn this. You should be able to look at this ODE and just write down a formal solution, but just knowing what the Green's function is for this kind of differential equation. All right. So now, what I want to, if I look in this situation, what I see is, if I have this separation of time scales, if this is big compared to this, what we see is that this is evolving very rapidly compared to this, which evolves according to this time scale omega. Okay? Which means that under this approximation, I can approximate over this time scale that this is constant over the time scale this changes. And take this outside meaningful. This slide of chalk follows from this separation of time scales. And that's what's known as adiabatic elimination. That is to say, the dynamics of the excited state, probability amplitude, are evolving so quickly compared to the dynamics of the ground state, which has to get out and it's gotta move out of the ground state up here. It's so slow because it's got such a sluggish Rabi frequency compared to these time scales that it's slaved to the dynamics. It'd like to change faster, but it can't because this term is being dragged along. And so in that case, we say that the dynamics of this are slaved to the dynamics of that. It's exactly like something you may have learned about known as the Born-Oppenheimer approximation in chemistry, where you have these big, fat, sluggish nuclei that can barely move, and the electrons are just so light, they're flying around, that the motion of the nuclei are slaved to the electron clouds. They adiabatically follow what the electrons do. In this case, the ground state probably amplitude is slaved to the ground state. All right, so now we can write down under this approximation of adiabatic elimination which is a good approximation when this is true, then we can now integrate this. Let's do it over here. And we get that the ground state, the excited state probability amplitude is approximately 1, you don't have to get the sign right if I try to do something above there. Right. So I have to have the denominator. So that's the solution to that differential equation under the adiabatic elimination case. Okay? So now I'm going to look at the initial conditions where I start in the ground state, where there's no probability in the excited state, and I get this relationship here between those. And now I get a differential equation for the ground state, which is the following. So I plug this back into this equation, and I get an equation for the ground state evolution, which looks like this. Plugging that back in.
In that approximation where you take the CG of T outside the
Yeah.
integral, you could also replace it by CG of 0 or CG of T over 2.
That's a much coarser approximation. The CG is not going to, otherwise then CG would just be static. What I'm saying is that CG is going to evolve, it's just evolving much more slowly. And it evolves, as we see in time scales here, that are related to omega squared over delta. Yeah?
Why is the I also in front of the gamma over 2 now? With the parentheses?
There shouldn't be. Thank you. Sorry. That's correct. So this should be here. Sorry. So let's look at this differential equation. What we see is, there's some coefficient out here, and then something with a time-dependent term, but that time-dependent term is extremely rapidly varying compared to this when omega is big compared to, when delta is big compared to omega. So again, in that adiabatic approximation, in the same way that we did for the rotating wave approximation, the rapidly varying terms in a differential equation with time-dependent coefficients play a small role compared to the static terms if they're oscillating very fast.
Is that another way of seeing why you want to pick T instead of T equals 0? Because in the CGSD, because
Yes.
in the beginning, early T bars, It's fast oscillating compared to when it's approaching T, when T prime is approaching.
I think that's fair. I mean, equivalently, if I have a gamma in here, what we're looking at is a situation, this is equivalent to saying that C sub E comes to steady state very quickly, even before anything happens with omega. As long as gamma is huge compared to omega, then this is going to reach steady state. I can set this equal to 0, and I got exactly what I wrote. So let's look at that equation now and see what we have. Well, we have this thing then, if I put the denominator up front by multiplying it by its complex conjugate, what I get is the following. So, you remember from last week, we called this thing the saturation parameter. The saturation parameter tells us in a two-level atom what is the population in the excited state, given a certain Rabi frequency and detuning. When the saturation parameter is small, the probability to be in the excited state is small and is equal to S over 2. Okay? So this equation should be written in the following way. There's an energy level shift that determines this and a decay term, where this is known as the light shift. We'll talk more about that now. And this, as we saw in the last lecture, or didn't, but you should have read it, is what's known as the photon scattering rate. I want to emphasize some points here, important points. So notice the nature of this equation and its similarity in some respects, ignoring the driving term, to this equation. It has a term that is got a phase with some energy or frequency scale and a decay. It says that the excited state, the relative frequency scale is detuning, and the relative decay rate is 1 over the lifetime. Once we've done the adiabatic elimination, we've put that now into dynamics on the ground state. Notice that there is a new energy scale here, which I'm calling the energy scale that is known as the light shift. I'll explain what that means in a moment. It's some energy scale associated with the effect of the light on the atom shifting the energy level of the ground state. Okay? This is also known as the AC Stark shift. You may remember the Stark shift is a kind of standard problem you study in perturbation theory and quantum mechanics. It tells you how the energy level of, say, hydrogen is shifted in an electric field. This is the shift of the energy level not due to a static electric field, but to an oscillating electric field. That's why it's known as the AC Stark shift as opposed to the DC Stark shift. Okay? And so this energy scale here is saying something that the energy of the ground state is shifted in the presence of the laser field by this amount. And thus there is a phase accumulated on the probability amplitude, which is that energy in units of h bar. So this is like a new energy eigenvalue. It's the perturbed energy of the ground state. In addition, the ground state kind of now has a finite lifetime. Why does the ground state now have a finite lifetime? And that lifetime means that there is a decay rate, which I'm calling the scattering rate. What is that about? Any thoughts? Why would the ground state no longer have a finite lifetime?
Is it because it can bounce through that virtual planet?
Yeah, so there is some, it's going up here, but it can spontaneously emit. Now, the rate of spontaneous decay depends on the probability to be in the excited state. So the rate at which this thing happens, the scattering rate, is the probability to be in the excited state times the rate of spontaneous emission. But what's the probability to be in the excited state? It's the saturation parameter over 2. So that's what this is, as we solved last week. So in this picture where we're off-resonantly driving the system, what we see are two important effects. One is that this level is shifted in some way. That shift is known as the AC start shift or the light shift. In addition, this thing now has a finite width to it because it's, in some sense, has a little bit of excited state character in it. Okay? Now, there's another way to think about this light shift in something beyond this adiabatic elimination, which was appropriate in this limit. I guess before I do that, I guess I want to look a little bit more at the nature of this. Let me write again. The saturation parameter if I'm far off resonance compared to the excited state line width or spontaneous emission rate. So if this is what we would say is far off resonance. That's a different approximation than adiabatic elimination, although they're intimately related. Because I can also adiabatically eliminate right on resonance as long as gamma is big compared to omega. But but if I'm far off resonance and I have a weak driving, then this is the scaling of the saturation parameter with detuning, which goes like the intensity, because the Rabi frequency is proportional to the electric field, the Rabi frequency squared is proportional to the intensity over the detuning squared. Okay. So, what that tells me then is that the light shift, how does it scale with detuning when I'm far off resonance? Well, it scales like the saturation parameter times the detuning, which means that this goes like the intensity over the detuning. Whereas the scattering rate, how does it scale? Well, this scales like the intensity over the detuning squared. Which is to say that if I go sufficiently far off resonance with a sufficiently big intensity, I can make the light shift arbitrarily large compared to the scattering rate. This is, for example, how you make an optical tweezer. You would make a focused laser beam that is extremely far from resonance, which creates a potential, which is the energy shift that varies with the function of intensity, but it can be a conservative potential if it's sufficiently far from resonance, because the dissipative part of the potential depends on absorption and emission, and that falls off very rapidly. So we typically want to manipulate this kind of coherence with high intensity far off resonance. All right, very good. So now let's look at the light shift in a little bit more detail. I want to talk about what are known as dress states. We mentioned this, I think, once before, but now I want to talk about this in more detail. So let's write down our Hamiltonian for the 211. I believe I skipped all this stuff. What was he thinking? Anyway, obviously he wasn't. So we have our Hamiltonian once again. Oh, I'm going to do this without the dissipation. As I say, this is relevant if I'm sufficiently far off resonance, for the reason that I just described. Then I can forget about dissipation over the time scale I care about. So my Hamiltonian is this. Which is written in terms of the Pauli matrices. I have to factor out the trace. Then I have the sigma z term and the sigma x term in terms of the pseudospin. Okay? We've typically been ignoring this term. It's irrelevant relative to what the energy levels are, but I'll keep it in here if I want to think about the shift relative to some absolute ground state, which I'm calling energy zero. Okay. So the dress states are, this of course is the atom plus the atom-like interaction in the rotating frame, in the rotating wave approximation. Okay. So this is the total Hamiltonian of my two-level system, including the interaction, which is here. Right? This is the thing that couples the energy levels, E and G. Otherwise, the eigenstates would be E and G. But now they're not the eigenstates anymore, because they're coupled together. However, I can ask, what are the new eigenstates of the system? Now, you may have done this using perturbation theory. We can ask, how are the energy levels perturbed by a weak interaction? And we should get back this, because this was effectively a perturbation theory kind of thing, because we didn't get. But we can solve this problem exactly. You don't need no stinking perturbation theory. Let's do the whole thing. I ask you, what are the new eigenvalues? What are the eigenvalues of this Hamiltonian? So the dress states are the eigenstates of the atom, including the atom light or atom laser interaction. So what are the eigenvalues?
You can use your formula that you said was so important.
Yes,
No.
yes, absolutely. We should do that. We have a two-level system. If we have a two-level system, we know what the energy levels of, we can diagonalize this in our head. You ready? So I'll give you a little head start. Right? Are you with me? So now I ask, what are the eigenvalues of this Hamiltonian?
It's negative 20 squared delta over 2 plus or minus
Plus or minus h bar over 2, the magnitude of this. Right? Which is equal to minus h bar over 2 plus or minus h bar over 2, the square root of omega squared plus delta squared, the total Rabi frequency. We love that. We love that formula. Yep.
Are we still under the constraint of delta being much greater than?
No, we're not. This is general. This is just the eigenstates of the system. All right. What are the eigenvectors?
Thing with the cosines.
Yeah, they're spin up and spin down along this direction in space, right? So there is some direction on the sphere that is h. This is theta. So tangent of theta is that.
Maybe you mean theta is measured from the z.
I do. This is still true. And, you know, cosine of theta is the omega over the square root of that, and the sine of theta. This one is the sine. The cosine is minus delta. And the spin up and spin down are cosine of that angle times g plus the sine of that angle over 2e. And the spin down is sine theta, or cosine theta over 2e minus sine theta over 2e. We diagonalized it in our heads. These states are known as the dress states. And this is known as the AC start change. Well, this is the AC start change. This would be the energy levels without. So let's see what this looks like. It's a little bit confusing because it's in a rotating frame. So it depends on the sign of the detuning. Okay? So you have two different pictures here. I'll talk about red detuning, in which case the detuning is negative, or blue detuning, which case is positive. So for red detuning, what we see in this case is that the lower state is without any coupling to the laser, but in the rotating frame, E is above G by an amount depending on the magnitude of the detuning. Right? Because E is spin up and G is spin down. And when this is a positive number, then in the absence of this guy, then the lower energy state in this guy is spin down. Okay? By an amount that's equal to the detuning. And we see that right here. Right? This is the positive energy. Now I turn on the laser, and what happens to this guy? This guy gets shifted down, this guy gets shifted up. And the splitting between these guys is now equal to actually, the one guy goes up and one guy goes down, but the splitting is this. Okay. So I have repelled these levels by an amount depending on this. So let's look at the difference in this energy. Let's look at what this energy eigenvalue is, the shift in this energy. Let's look at the shift of the energy of the lower state. Okay? That's the shift of the ground state. According to that, that's equal to minus this over 2 minus h bar over 2, the square root of omega squared plus delta squared. This is minus delta is equal to the absolute value of delta when delta is negative. Those minus signs drive units. Now, let us look at this in the limit that we were discussing, where my Rabi frequency is small compared to the detuning. That's the limit that we saw where we did adiabatic elimination. That's the limit of perturbation theory, where this is thought of as the 0th order Hamiltonian, and this is the perturbing Hamiltonian. So the regime of adiabatic elimination is also the regime of perturbation theory. So now, if the limit that omega is very, very small compared to the magnitude of delta, then I'm going to be able to do a Taylor series expansion on this. the square root of delta is squared is the magnitude of delta. So far, I haven't done any approximations except factor out the delta. And now I'm going to do approximation. When this is very, very small, then what is this thing equal to? Then I can just do that, right? And so this then is equal to and minus, oh no, 1 power delta is gone. And minus the magnet, and for red detuning, this is equal to this. Which is equal to which is what we had before. Good. So what we see here is that when we have red detuning, the ground state is shifted to a lower energy by an amount just as we expected in the perturbative limit, but more generally is of this form. Okay? In the opposite case, so I'm just going to write this down here. For blue detuning, the opposite is true in the rotating frame. Now, this gets shifted, this is the ground state at 0 energy, and the excited state is shifted down. They're still split by this amount. But this was 0 energy, and this guy is shifted down by the amount delta, when delta is a positive number, right? That's in the opposite, in the case where I have no, now I turn on the laser, and I get this splitting. Same splitting, but now you notice that the ground state is pushed to a higher energy state, and the excited state is put to a lower energy state. Which means there's a certain jargon people use in the field that for red detuning, the ground state is a strong field seeker. It goes to lower energy where the field is bigger because its energy is lower. And in the blue detuning, the ground state is a strong field seeker. A weak field seeker. It tries to go to where the field is weaker, because it goes to a lower energy state where the field is weaker. So for blue detuning, the atoms are trapped in the dark spots of the light, and for red detuning, they're trapped in the bright spots. So if you want to make an optical tweezer, you better be red detuning. If you want to make a bottle beam trap, you want to be blue detuning. Yeah.
What happens if you pass through delta equals 0?
There is no shift at delta equals 0. There's no line shift.
I mean, but what happens if you adiabatic, like you start?
Good question. Well, I think you're studying some of that stuff for homework right now. So if I were to look, interestingly, let's look at these energy levels as a function of detuning. Okay. And if I look at this, let's look at these energy levels. First, without any laser on. Without any laser on, what we see is that the excited state looks like this, and the ground state looks like that. This is with no laser. The ground state has, it's not even in this expression. The excited state looks like that. To the red of resonance, the ground is below the excited. To the blue of resonance, the ground is above that. This is in the rotating frame, of course. Now I'm going to turn on the laser. What happens to this diagram?
Crossing
Becomes an anti-crossing, an avoided crossing, right? These are the new eigenvalues. And so to the red, first proper use of color, I get that energy level. Please, 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 where's the blue? The only thing we have bluer than red is orange. We get that, right? So what you see here is, so this adiabatically connects to the ground state. So if I start here, the ground state is shifted down. On this side of resonance, the ground state is shifted up. Now, if I were to sweep and I prepared the system, I would adiabatically follow, and that's known as adiabatic passage. I would completely transfer the ground state to the excited state. One of my favorite things to do these days. Yeah?
What happens if you start at delta equals 0 and then go one way or the other?
Well,
Is there
the question is about adiabatic following. This is a picture of what the energy eigenvalues are. Okay? Now, the dynamics of the system depends on the Schrodinger equation. So you have to ask, are you in an eigenstate of the Hamiltonian or are you not? If you're in an eigenstate of the Hamiltonian, then you don't do nothing because you are a stationary state. But if you are not in an eigenstate of the Hamiltonian, well then, you know, you're not a Neanderthal, you'll evolve. And you'll evolve in time according to the Schrodinger equation. So if I turn on the Hamiltonian and I start in the ground state, what's going to happen to the system? Right on resonance. I turn on the laser.
turn on abruptly?
Yeah. It'll probably oscillate. I mean, I'm in the ground state, but that's not, the eigenstates are the symmetric and antisymmetric cases, so I roughly oscillate. Okay? So to do this kind of picture involves starting in an eigenstate, slowly turning on, changing the detuning and the amplitude in such a way that I stay in an instantaneous eigenstate of the system. And I have to change the detuning slowly. That's known as the adiabatic approximation, such that I always stay instantaneously in the eigenstate, and that's what we require. Very good. What about the stress states themselves? Let's look at these guys, what the eigenstates are. So if I look here at, say, the dressed ground state, as we said, if we're somehow to get right on resonance, we would make an equal superposition of them. But if I'm far off resonance, and if I'm also in the limit where this is very, very small compared to the magnitude of delta, then theta is approximately equal to that, right? Which is much, much less than 1. In that case, my stress ground state is approximately equal to in that case, oh boy, which one is the ground state in this case? I mean, it's really this guy. I'm trying to figure out what's going on here. Ah, I see what's going on. This is spin up, which is, and this is spin down, which is G. This is spin up. Now it makes sense. Good. So this then is approximately equal to cosine the lowest order is G minus beta over 2 E, which is equal to minus omega and for red detuning, minus delta, magnitude delta is delta. So what I see is that the dress state is has a small admixture, or what we say really superposition. I've taken a little bit of ground state and mixed it in, or superposed it in with the excited state. And this is exactly what you would get from first order perturbation theory. If you recall perturbation theory from your studies in advanced quantum mechanics, the perturbed energy level involves the matrix element. Do you remember that formula? You have the zeroth order eigenstates, and then you have the energy denominator, which tells you something about how much you change that level, right? In our case, the interaction is the dipole interaction, and that's just this term. And the energy denominator in the rotating frame is the detuning. And so this is what is expected as we solve the problem exactly in this two-level system. We can diagonalize it, but we must recover the perturbed solutions, which are the limit that the interaction is small compared to the zeroth order interaction, which in this case is equivalent to saying the Rabi frequency is small compared to the detuning. So that's in the tails of this distribution. All right. I think we will call it quits for now, and we'll pick up where that edited video stands.